I I hope everyone can see my screen.
Yeah, we can see.
Okay. All right. Thank you. So, like I it was introduced, I will be speaking on the geometry of manifolds and the Gauss-Bonnet theorem. And the following is the outline of this talk. We'll be obviously be looking at the objects of Gauss. Then we'll talk about the structures on a differentiable manifold, after which we'll talk about connection and curvature of manifolds. Then we'll talk about the main theorem of this presentation, which is the Gauss-Bonnet theorem. And finally, we'll look at an application of this Gauss-Bonnet theorem, the concrete application on one two-dimensional manifold, which is the sphere. Okay, so the main object of this course, which is the differentiable manifold. So we're going to build it up little by little. But first and foremost, what is a topological manifold? Simply put, a topological manifold is a topological space that is locally Euclidean. And what do we mean by locally Euclidean? It means that at a very local level, that is, for each point, when we are at that point, it looks as if we are simply in a Euclidean space. So we can consider, for instance, being on the Earth as a point on the surface of the Earth. Generally, we all know that the Earth is known to be spherical in shape, but it is locally Euclidean because it's locally flat. When we are on the surface of the Earth, it doesn't seem as if we are on a spherical surface. And it is one of the reasons, one of the easiest way to see that the Earth, which is a sphere, is actually, you can even consider it as a manifold. So broadly speaking, topological manifolds are topological spaces that are locally Euclidean. But if we want to look at it formally, the definition of locally Euclidean, it means that for every point in the topological space, there exists a neighborhood, an open neighborhood U, and a homeomorphism between that open space U, open set U, and an open subset of a Euclidean space, say Rn. That is the formal definition of being locally Euclidean. These homeomorphisms are what we refer to as charts. And a collection of these charts is known as an atlas. And that right is the definition of a topological manifold. But interesting manifolds, differentiable manifolds. Again, broadly speaking, differentiable manifolds are topological manifolds that are endowed with some special structures that allows us to generate or generalize the calculus we know of Rn to manifolds. So a differentiable manifold is a topological manifold that we have endowed with some important structures. And to graduate from a topological manifold to a differentiable manifold, we need to look at transition maps. So looking at the, sorry, please. Okay, so looking at the diagram we have on the screen, if we consider this here as a manifold, a topological manifold. When can we call it a differentiable manifold? So if at a point we have an intersection between two open sets, two open neighborhoods that contains that particular point, we define the transition maps from phi to psi as follows. We know that there is a homeomorphism between U and an open subset of Rn. So we consider this an open subset of Rn. And this V hat as another open subset of Rn. So if the connection that goes from this to this is called the transition maps. So it is simply a phi inverse as we go from here to here first and then to here. So phi inverse, then afterwards we do psi. So if this map is differentiable, then we say that the topological manifold is a differentiable manifold. And this gives a differentiable structure to our topological manifold, making it a differentiable manifold. So if all the transition maps as such are smooth, we regard our topological manifold as a differentiable manifold or a smooth manifold. Then we can look at the formal definition here. So let M be a Hausdorff topological space which is second countable. M is said to be an n-dimensional differentiable manifold, Mn, if there exists a family of open subsets UA, that is, we are indexed it by set A, and for each A in A, there exist homomorphisms phi A from a subset, an open set of the manifold to open sets on Rn. So where VA above in Rn, such that the open set UA cover M. That is, the union of all these open sets give us M. And for any pair, the transition maps, okay, is a diffeomorphism. That is, it is smooth and it has smooth inverse. This gives us a differentiable manifold. The most basic example of a manifold, a differentiable manifold, is the Euclidean space Rn itself. So it is a topological manifold because itself, it's not as if it looks like a Euclidean space. It is already a Euclidean space. Then the charts in this case will be the identity map, since it just takes us from Euclidean space to an Euclidean space. So it is a differentiable manifold because the identity map, we know that they will constitute the transition maps here, and it gives us a differentiable manifold. But the concrete example that we are going to give here is that of a sphere, because it is the main object that we're going to base our talk on today. So a sphere Sn, which is the set of all points Rn plus 1 in Rn plus 1 that satisfies this property. So the summation of the square of the component will give us 1. This is Sn and is embedded in Rn plus 1. We can consider Sn, the sphere, as a topological manifold because we look at the two open sets U1, U2, which are simply the sphere without the north pole and the sphere without the south pole. These are two open sets. And the maps that we'll consider here are simply that of the stereographic projection. So in this case, there are two maps. One that maps all the points on U1, that is the sphere minus the north pole, minus the south pole rather, and the sphere minus the north pole. So the stereographic projection, as you can see in the diagram, maps each point to this Rn. So the diagram is just depicting So although the diagram is showing the sphere S2, we can use it to understand the general Sn. So the map projects points on the sphere to a point on Rn. So the first one, phi 1, given by 1 over 1 plus naught x. And phi 2 is given by x 1 over 1 minus x naught times x, where x is a component that has dropped the x naught. This is a topological manifold because, of course, these are homeomorphisms. But is it a differentiable manifold? That is what we see in the next space, in the next screen. So we can obviously see that U1 union U2, you will give Sn, and the phi i's are homeomorphisms. And the transition map, which goes from Rn minus 0 to Rn minus 0, is given by this map. And obviously, it is a smooth map. Okay? It is differentiable, and it has a smooth inverse. So this makes the sphere a differentiable manifold and not just a topological manifold. Now, having discussed um, what a differentiable manifold is, since we have differentiable structures on differentiable manifolds, this allows us to define the concept of smooth functions on them. So what is a smooth function on a manifold? If you have a manifold M of dimension K, of course, we know that there is a homeomorphism between the subsets of M and Rn. So if we define f on a manifold, that function f is said to be smooth. So we don't know anything about the differential or if something is smooth on a manifold, but of course, we know the concept of differentiability between two subsets or two Euclidean spaces. So we'll connect this Euclidean space and this Euclidean space. So the function f, which goes from M to Rk, is said to be smooth if this composition f of phi inverse is smooth. Of course, in the usual sense of differentiability between two Euclidean spaces. While a function between a map between two manifolds M and N are said to be smooth if the composition that goes from this subset of Rm to this subset of Rn is smooth in the usual sense. More formally, we can define it as follows. So a function f from M, the manifold M to Rk, is said to be smooth if for every chart U with homeomorphism phi on M, the composite function f composed with phi inverse is smooth on the open subset of Rn. And given two smooth manifolds, M, U, and NV, a continuous map f from M to N is said to be smooth if this composition is smooth in the usual way. And a map that is smooth is called a diffeomorphism if, in addition to being smooth, its inverse is also smooth. And in that case, M and N are said to be diffeomorphic. Now, we look at some differential or some structures on a differentiable manifold. And first of such that we are going to talk about is the tangent space. So the concept of tangent space to a manifold at a point helps us to understand linear approximations on differentiable manifolds. So the tangent space of M at a point P, which is usually denoted by TPM, is a set of all derivations of C infinity functions at P. So we actually represent the set of all smooth functions on a manifold by C infinity M. So, and what is a derivation of a smooth function? This derivation of a smooth function is simply this a linear function, a linear map that satisfies the Leibniz rule, that is the product rule. So if we gather together all such derivations of smooth functions at a point P, we get the tangent space at that point. There are different ways to define the tangent space, but for the purpose of our discussion, this is the best way of defining it. So for each point, there is a tangent space. And as an example, since we have said that the main object of discussion or example that we'll be looking at as differentiable manifold in this presentation is that of the sphere, we can see that at every point there is a tangent space which is just a plane on the sphere. So the next result shows a relationship between a manifold and a tangent space at a point on it. For all points in a manifold and any local chart such that P is in the neighborhood U, the set of the tangent vectors, that is these coordinate vectors, from 1 to n, they form a basis for TPN. And what does this mean? This implies that the manifold and each tangent space has the same dimension. So the dimension of the manifold and the dimension of the tangent space at each point has the same dimension, which is n. And since for every vector space we have the notion of dual vector space, the same way we can talk about the dual vector space to the tangent space at a point P. And this is called a cotangent space at P, denoted by TP star M. So as the usual dual vector space, this is the space of all real valued linear functionals on TPM. And these are called covectors at P. But in order to study the geometry of the entire manifold, it is not enough for us to just look at the tangent space at a particular point P. We need to see the tangent space of the entire point on the manifold. And this is a reason for us to look at what we call the tangent bundle. So we define a tangent bundle, which is a way to define or to glue together tangent spaces smoothly in a way that respects the underlying structure. So the tangent bundle of M, which is denoted as Tm. So this time around, we are not putting the P because we are looking at the tangent space of all the points together. So Tm, to be the disjoint union of the tangent spaces at all points P in M. So we are gluing together, patching together all the tangent spaces of each point on M. So it is the disjoint union. The tangent
Ayodeji,
bundle can be shown. Yes, please.
I have one question here about tangent bundle. You are saying like you are taking this giant union, and also you are saying you are gluing this thing. So how it makes sense if you are taking this giant union and it's gluing? What is the gluing actually? What is the identification?
Okay, so let me give a very simple case. So if this is a whole space, these three subsets are disjoint. So this A1, A2, and A3 are disjoint. And we can simply say we are gluing them together to form the big, it's just like a partition of a particular space, such that by the time we find the union of these partitions, we get the entire space. So if we take the disjoint union of all the tangent spaces at a particular point P, we get a tangent bundle. I hope it explains what it answers your question.
Thank you.
Yeah, thank you. Thank you for the question. So as I was saying, the tangent bundle can also be proved to have the structure of a differentiable manifold itself. Okay, you know that the tangent bundle is a collection of tangent spaces to points on the manifold. But we can also prove that the tangent bundle is a differentiable manifold with dimension 2n. Dimension 2n. All right, then that's the first structure. But for all p, we can also take the disjoint union of the cotangent spaces. And this gives us the cotangent bundle of M, which is also denoted as T star M. Now, the next thing we'll look at, but before we go on, we should note that the tangent bundle and the cotangent bundle, they are special examples of a vector bundle, which is generally just a collection of vector spaces. Okay, the collection of vector spaces that vary continuously over a topological space. In particular, the cotangent bundle is defined, like I said, to be the dual vector bundle to the tangent bundle Tm. So next we'll talk about the vector field. A vector field X on a smooth manifold is a map that assigns a vector, a tangent vector xp to each point in M. So we take a point on a manifold and we assign a tangent vector to it. So it does that to all the points on the manifold. And in local coordinates, a vector field can be expressed as follows, where each AI is a function on a coordinate neighborhood u comma x. So this is a tangent, a vector field. So it takes a point on the manifold and assigns a tangent vector to that point. So the collection of all the vector fields, the set of all the vector fields is denoted by this symbol, this curly X on the manifold. And you see, this set of all smooth vector fields it has an algebraic structure, which is a C infinity module. So defined with the usual component-wise addition and scalar multiplication by smooth functions on M. So it is a C infinity module, but not just a C infinity module. It means, so when I say C infinity module, I mean if we add two vector fields together, we get another vector field. Again, if we multiply a vector field by a C infinity function, we also get a vector field. But what about multiplying two vector fields together? So there's a special way to get a vector field when we multiply them together, and that is the essence of talking about the Lie bracket. The Lie bracket is a special way to uh, uh, multiply two vectors and still get a vector field. I mean, multiply two vector fields and get a vector field. So it is defined as follows. So in this way, we are sure that the Leibniz rule, the product rule, is still going to be satisfied. So after talking about this, we can now look at another structure on differentiable manifold, which are the differential forms. The space of forms provides geometric and topological information about the manifold, such as the orientation, volume, and so on and so forth. So they simply generalize vector fields to higher dimension. They bridge the gap between geometric concepts and analytical techniques. And in fact, they allow for integration of geometric quantities over manifolds. Like I said, they generalize vector fields to higher dimension. We know what vector fields are. For each point, we assign a tangent vector. just a single tangent vector. But what a K-form does is to assign a multilinear map to a point on a manifold. So in formal definition, we have that a differential K-form is a tensor field whose value at P is an alternating tensor. So when we say a tensor is simply, it's just in basic term, a multilinear map, a map that is linear in each, individually in each component. And the local expression of a K-form in any coordinate chart is given as follows, where the I is an increasing K-length multi-index. And what do you mean by a K-length multi-index? So, for instance, if we are dealing with if you are in 5-dimensional manifold, for instance, or let's say 4-dimensional manifolds. So I1 to IK is a multi-index that is increasing. So we have something like I1, I2, I3, I4. We have something like I2, I3, I4. So depending on the length we are talking. So if we are just talking about length 3, we can have something like I1, I3, I4, I2, I3, I4, and all these are the coordinate chart, or what the forms that follows the expression of a K form. Then next we'll talk about is the Riemannian metric. Riemannian metric provides a notion of distance at each point. It allows us to find lengths of tangent vectors, angles between tangent vectors, and volumes of manifolds, and so on and so forth. So a Riemannian metric on a differentiable manifold is a positive, definite, symmetric two-tensor field. So when we say two-tensor field, we are just saying that it takes in two vectors. So M, that is a manifold that is endowed with a Riemannian metric, is referred to as a Riemannian manifold. And in local coordinates, a Riemannian metric can be expressed as follows. So where the GKL is a positive semi-definite matrix, which is made up of smooth functions GKL. So as a basic example, we can consider the smooth manifold, the Euclidean space Rn. So the usual dot product on TXRn for each x in the Euclidean space Rn is called the Euclidean metric. And it is nothing but the standard scalar product on Rn. So in this case, the smooth functions JKL are simply the chronicle delta ij, that is, we have the matrix to be the identity matrix. This important result is telling us that there exists a Riemannian metric on every differentiable manifold. And to prove this, we only need to show that to use the partition of unity to glue together all the metric that is available by the embedded or homeomorphisms between the manifold and the Euclidean space. Since we know that there is a Euclidean metric on the Euclidean space. Then next we talk about connection on manifold. A connection on a manifold provides a way to differentiate vector fields along curves on a manifold. And formally speaking, given a differentiable manifold, a connection in a tangent bundle TM is a smooth map that takes in two vector fields and produces a new vector field, such that it satisfies the following properties. That is, it is linear in the first the first entry, that is, it is C infinity linear for every connection fx plus gx tilde y is equal to f connection, or we can also call this covariant derivative of y with respect to x, just like we have our usual dy then plus g covariant derivative of y with respect to x tilde. So it's like we are differentiating y in the direction of fx plus gx tilde. So it obeys, it is C infinity linear. Then B, it is also linear in the second component. And finally, it satisfies the product rule as follows. That is connection of manifold. And the next is to talk about the Christoffel symbol. If we have EI to be a smooth local frame for TM, a tangent bundle TM, the vector field, that is the covariant derivative of one of the component of the local frame, EJ, with respect to EI, can be expanded as follows, where each of these are called the Christoffel symbols of the connection. And for an n-dimensional manifold, we are going to have n raised to power 3 of them because we have 3 indices here, I, J, K. So these are called the Christoffel symbols of the connection. And the Christoffel symbols completely determine the connection. So if I want to know about a connection, I only need to compute the Christoffel symbols. Every tangent bundle admits a connection. And just like we said that every manifold admits a metric, every tangent bundle admits a connection, and the proof of these use the same tool. We just need to patch together using the partition of units. Then we have seen that every manifold has a connection, has a metric, and every tangent bundle admits a connection. But there is a unique connection for every Riemannian manifold, which is determined by the following properties. The first one is the compatibility with the metric. So let M, G be a Riemannian manifold. A connection on M is said to be compatible with a metric if for all vector fields X, Y, and Z on the manifold, we have that this holds. So the covariant derivative of the product of y and z with respect to x is equal to the product of the covariant derivative of y with respect to x and z plus the product of y and the covariant derivative of z and x. So this defines the compatibility of a metric with a manifold. And the second property, but the metric connection actually provides a way for us to differentiate vector fields on the manifold while preserving the metric structure. So the underlying metric structure on the Riemannian manifold is preserved. Then also we talk about the torsion. The torsion is simply a measure of the failure of a connection to be symmetric. So it is defined as follows. So if it is symmetric, we know that we can do xy and yx and we'll get the same thing. So, but the torsion measures how far away from being symmetric it is. So, and as we can see, a connection is said to be symmetric if this is 0. So if this is 0, then we'll see that we can carry this to the other side, and we get that the Lie bracket xy, the commutator of xy, is equal to the covariant derivative of y with respect to x minus the covariant derivative of x with respect to y. Equivalently, we can also say that it is symmetric or torsion-free if the Christoffel symbols ijk is equal to the Christoffel symbols we have jik for all ijk. Now, since we define these two properties, we can look at the unique connection for every Riemannian manifold, which is given by this result by Levi-Civita. So if we have a Riemannian manifold Mg, there exists a unique connection on M which is compatible with a metric G and also symmetric. And this special connection is what we call the Levi-Civita connection. And since we said that the Christoffel symbols completely define a connection, we look at the Christoffel symbol of the Levi-Civita, which is given by this formula. And as you can see, it is simply defined only on the partial derivatives of the components of the metric tensors. So for Levi-Civita connection, we only need to get the partial derivative of the components of the metric tensor. Now, finally, we can talk about the curvature on differentiable manifolds. So the curvature tensor captures some geometric properties of the Riemannian manifold, the intrinsic geometric properties. So it measures how the manifold deviates from being flat or Euclidean. Formally speaking, the Riemannian curvature of a Riemannian manifold is the tensor, that takes in three vector fields and is defined as follows, this map. So it is actually a 1-3 tensor, takes in three vector fields and produce one vector field. So and we can write this as follows in local coordinates. And in terms of the Christoffel symbols, the Riemannian curvature is also given as follows. So the components of R are expressed with this expression. So for easier computation, we can also consider the Riemannian curvature tensor instead as a 1-3 tensor. We can consider it as a 0-4 tensor by bringing down one of the indices, by lowering the indices, such that we have all of them lowered. And why do we do this? In this format, some symmetric properties will always show up. It will manifest. And it helps us to reduce the number of computations we need to make for us to calculate the curvature tensor. Finally, we talk about the sectional curvature. So if we are on any manifold of any dimension, the sectional curvature is simply the curvature of a two-dimensional plane within the Riemannian manifold. Or if we take any two tangent vectors, linearly independent vectors, and we take the plane spanned by these two linearly independent vectors, the curvature of that two-dimensional plane is what we know as the sectional curvature. So if this sigma is the plane that is a subset of the tangent of space at P, generated by mu or U and V, we define the sectional curvature of that plane as follows, using the curvature tensor and the parallelogram here. So for a surface which is two-dimensional manifold, we know that it is already a two-dimensional manifold. So the sectional curvature is known as the total curvature because there is no subspace of it that is it is already a two-dimensional manifold. So the sectional curvature is known as the total curvature or the Gauss curvature of the surface. And finally, to the main theorem of this presentation, which is the Gauss-Bonnet theorem. It is a fascinating result, which I particularly find fascinating because it relates geometric information of the surface in terms of the curvature to the topological structure of the surface in terms of the Euler characteristics. So most of the things I've worked on in the past, they are always finding links between two seemingly different areas of mathematics. And this time around, we are looking at a link between geometry and topology. So what does the theorem state? It states that suppose M is a differentiable compact Riemannian manifold of dimension 2, then the integral of the Gaussian curvature over the volume form is equal to 2 times pi times the Euler characteristic on M. So where K is the Gaussian curvature and dA is the volume element of the manifold. So the Euler characteristic is one important topological invariant, which is mostly studied in algebraic topology. And in algebraic topology, we look at the Euler characteristic to be given by V minus E plus F, where V, E, F respectively stands for the vertices, the number of vertices, the number of edges, and the number of faces on any admissible triangulation of the manifold. Okay, it can actually be proved that every compact manifold admits a triangulation. So looking at these triangulations and calculating all the vertices, edges, and faces to get the Euler characteristic. So we are saying instead of going through the stress of looking for vertices, edges, and faces, if we simply know the Gaussian curvature, integrating the Gaussian curvature simply helps us to get the Euler characteristic. Now we can now look at this example on a sphere. So all the things we've been discussing, we want to look at how it applies to a sphere S2 embedded in R3. So the stereographic projection provides a conformal equivalence between the Euclidean plane Rn and Sn minus a point. So in particular, R2 and S2 minus a pole, such that we go from XYZ to UV, X over 1 minus Z, Y over 1 minus Z. And the inverse phi inverse is given by this map. So next we'll look at the metric. The metric on R3, the standard Euclidean metric, can be proved back since S2 is embedded in R3. So it inherits the standard Euclidean metric on R3, and it gives us what we call the round metric. So this is just a calculation of a computation of how we pull back the Euclidean metric to get the round metric. So, and like we said, there is always a matrix representation of Riemannian metric. In this case, we can see that the representation is a diagonal matrix, which makes things really easy for us with the inverse Gij, so power Gij, also a diagonal matrix. So after looking at the round metric, we can also now talk about the Levi-Civita connection. And Levi-Civita connection, we know that it is determined by the Christoffel symbols. And you remember that we said the Christoffel symbols are simply calculated using partial derivatives of the component. So if we differentiate, if we get a partial derivative of these components that we have here, we get the following. So using the formula, we calculate the Christoffel symbols as follows. So as you can see, the symmetricity that we talked about. So when UV is equals to VU, and it gives us this, and UV equals to VU, also get it. Then finally, curvature on the round sphere. Putting together both the connection and the clear symbols and the formula we have defined earlier, we can calculate the curvature of the round sphere as follows. So bringing down the, lowering the indices, it saves us time in solving up to different components of the curvature tensor. And using the formula, we get that the curvature over u squared plus b squared plus 1 raised to power 4. Then finally, the sectional curvature using the formula we defined earlier is given by this, and we get that the curvature is equal to 1. It makes sense that the Gaussian curvature of the sphere is a constant 1. That is, it is constantly curved, and it is equal to 1. Now that you are gotten the curvature, we can use the Euler characteristic of the sphere, applying the Gauss-Bonnet theorem. So we recall that according to the Gauss-Bonnet theorem, the integral of the Gaussian curvature is equal to 2 pi times the Euler characteristic. So, and since the manifold here is just the sphere, we have the S2 written here. And since the curvature is also 1, so it means we are just integrating 1 over dA. And dA is just the total surface area of the manifold in this case. And since we are talking about a sphere, the total surface area of a sphere is 4 pi r squared. And since r, it is a unit sphere, it means the r square is going to be equal to 1. So we have 4 pi in that case. So the integral is 4 pi. It is equal to 2 pi times the Euler characteristic. And this that the Euler characteristic is equal to 4 pi over 2 pi, which is equal to 2. So simple, you are putting the Euler character of the sphere as 2. And this agrees with what is seen in algebraic topology. So for any admissible triangulation of the sphere, the number of vertices, the edges, and the faces satisfying V minus E plus F must be equal to 2. It's fascinating and interesting because not only can we just get the Euler characteristic, we can also get another topological invariant, which is the genus, which loosely speaking is the number of poles or handles attached to a manifold. And knowing the Euler characteristic, we know that the genus is 2 minus the Euler characteristic over 2. In this case, that will be 2 minus 2 over 2, which is equals to 0. And again, that makes sense because the sphere has no hole or handle. So the Gauss-Bonnet theorem is such a powerful theorem, very important ones in differential geometry. As you can see, it links the two separate aspects of mathematics, and it lays a foundation for the higher dimensional links. Thank you. These are my references for the presentation, and if there are any questions, can take a few of them before I run along for my next program.
Thank you so
Thank you
much,
very much for
Ayodeji.
listening.